All right, let's jump into chapter 10 for part 2 of respiration during exercise from our exercise physiology textbook. We looked at the anatomy in the lung in the last section. Now we're going to look at some more aspects of lung function. The way we assess lung function is through a process called spirometry. A spirometer is an instrument that measures the flow rate and therefore the volume over a period of time of air going in and out of the lungs. Here's a picture of a young fellow breathing in and out through a spirometer, which again can record those volumes and plot them on this chart recording here. A modern spirometer is an electronic device, a little less elaborate looking than this. There's probably reasons why they have him all ensconced in this chamber. And this is an electronic spirometer. But again, most spirometers are just a handheld device you hold in front of you and put the mouthpiece in your mouth and breathe in and out, and it will report on the inspired and expired volumes. So here's a sort of cartoonized, simplified tracing from a spirometer. These little tiny humps in the middle represent the volume of air during each resting inspiration and expiration. Inspiration and expiration. That's called the tidal volume. If you measure the amount of additional air that can be inspired, as much as you can possibly draw in, above and beyond the tidal inspiration, that's called inspiratory reserve volume. If you measure the maximum amount of air that you can possibly force out of your lungs after a tidal expiration, that's called the expiratory reserve volume. How much extra air can you push out? And if you add those three together, inspiratory reserve, the tidal volume, and the expiratory reserve volume, that's called the vital capacity. It's the total volume of air that you can forcibly control voluntarily. It's the difference between a maximal inspiration and a maximal expiration. That has some value diagnostically, clinical diagnostically, and we'll see in a bit. Another interesting thing to note looking at this spirometry graph is that there is always some air left in the lungs. The alveoli, like little elastic balloons, always must remain inflated. So even when you expire all the air you can possibly push out, the alveoli still are partially inflated. Think of how hard it is to start inflating a balloon that you take out of the package or that has no air in it. It's very hard at first, and then finally when it blows up, it just is easy to cause it to swell up and let a little out and in. That's how your alveoli are. You can't start them if they're completely collapsed very well. So we don't let that happen. The residual volume is that bit of air that stays in the lungs all the time in all those alveoli. So again, tidal volume, resting breathing volume. Inspiratory reserve volume, how much additional air can you inspire from tidal inspiration. Expiratory reserve, how much additional air can you expire after a tidal expiration, and the residual volume always remains in the lungs. Again, vital capacity is the total amount of volume that you can voluntarily move in and out of your respiratory system. These are other interesting volumes of capacities. Functional residual capacity is a clinically meaningful term because it includes the residual volume, but we won't really go into that too much. You can't measure those by spirometry. Anything that has the residual volume in there has to be measured by other kind of interesting and complex methods, since you can't breathe the volume out. Let's take a look real quick at something you should know about, and you may already know about it, hopefully not by anyone you've known. Chronic obstructive pulmonary disease is a combination of two terrible diseases, particularly emphysema and also chronic bronchitis. Emphysema is a progressive disease in which the alveoli are being destroyed. Their walls are just breaking down, and many clusters of alveoli are being just blown apart into larger, huge, air-filled chambers where the alveoli used to be. And it's reducing the surface area for gas exchange tremendously. Remember, we said the amount of gas you can get to diffuse across the respiratory membrane depends on the surface area. We're losing that surface area. Chronic bronchitis is inflammation. Histamine is being released, causing bronchoconstriction as well as mucus production, which produces a large increase in resistance to airflow. It's very hard to move air in and out of the lungs when you have bronchitis, and chronic bronchitis just means that it's been persisting for months of time for no apparent reason. You just have this lasting inflammation that just won't stop. Typically, cigarette smokers develop emphysema and have chronic bronchitis, therefore COPD. It's what often kills. If they don't get lung cancer, smokers, long-term smokers often get COPD or typically get COPD. How can we diagnose this condition with spirometry? Well, this is called obstructive disease, and the bottom line, the simplest description is it's hard to get the air out when you have obstructive disease. You can inspire air relatively easily. It's very difficult to force it out. So if we use the spirometer to see how much air someone can force out of their lungs in 1 second, we can figure out whether their lungs are obstructed or not. So in other words, have the patient inspire all the air of maximal inspiration, all the air they can fit into their lungs, put the spirometer device in their mouth, and then breathe out as hard and as forcefully as possible, and we'll calculate how much volume came out in 1 second's time during that effort. Then we'll divide that by the vital capacity and calculate a percent. That's how this forced expiratory volume in 1 second is expressed. It's expressed as a fraction of, or a percent of, vital capacity. It should be greater than 75% for normal lungs. If someone has emphysema or obstructive disease, here's the chart showing the expiration of air over time in seconds, liters of air over time in seconds, going out of the lungs in this forced expiratory volume measurement. Here's the difference when someone has obstructive disease. Look how long it's taking to get that volume out. So we would just get a number much less than 75%. Probably in this case they calculated 33% in 1 second. So right here we've only expired 33% of the vital capacity in that 1 second. So clearly something wrong. Now let's talk about something that will help us understand the driving force for gas diffusion. We're going to use a term called partial pressure rather than concentration to talk about gases, because gases are a little different than, say, typical solutes dissolved in water, although oxygen and CO2 do act as solutes. Dalton's law of partial pressure says that if you have a mixture of gases under pressure, each gas will exert a fraction of that total pressure in proportion to its percent in the mixture. So let's say in the atmosphere, we have a total of 760 millimeters of mercury gas pressure. In other words, piled on top of our heads right now is about a 1 mile high deep pile of air molecules, and they have mass. They're being held down by gravity, and they're striking us, they're striking everything in sight. And the bombardment of every surface is what we mean by pressure. It's force per unit area on the surfaces. So anyway, atmospheric pressure is 760 millimeters of mercury, and it's a mixture of gases. It's 21% oxygen. What fraction of that 760 millimeters of mercury partial pressure, or total pressure, is oxygen partial pressure? Well, if we take 21% of the fraction of oxygen in the air times the total pressure, we'll get 159 millimeters of mercury. That's the partial pressure of oxygen in the air at sea level. CO2, it's only 0.03% in the air. So when we multiply that times 760, we wind up with 0.3 millimeters of mercury partial pressure, I'm sorry. We're just going to call that 0. There's no CO2 in the air for the most part. Enough for plants to use for photosynthesis, but for as far as the human physiology, there's no CO2 out there. We're going to bring a lot of CO2 into our lungs because of cellular respiration and breathe it out into the air, and then bring in some fresh air that has no CO2. Most of the gas in the air around on the Earth is nitrogen. So 80%, a little bit less than 80%, 79% is nitrogen, so 601 millimeters of mercury partial pressure of nitrogen. We won't say another thing about nitrogen for a couple of reasons. One is it dissolves itself in all of our body fluids, but it doesn't have any role in respiration or in cellular function or anything, so it's kind of inert. It just sits there. So we don't need to talk about it in that regard. And also, it's not very soluble. So even though there's a large partial pressure of nitrogen, not very much can dissolve in the body fluids. So we don't really have a big deal. If you're going to scuba dive, then yes, you very importantly must consider the effects of nitrogen pressure in different tissues of your body at different depths in the sea. So thinking about the diffusion of oxygen and CO2 across the respiratory membrane, the walls of the alveoli and blood capillaries. We need to diffuse gas from the alveoli into the blood, oxygen mainly. We need to diffuse CO2 from the alveoli into the blood. What determines the amount of gas that can diffuse per unit time across that membrane of all the alveoli? Well, it depends on the surface area, the tissue area. The surface area of all the alveoli is an important thing that limits the amount of gas that can be exchanged. The distance of diffusion. The thicker the respiratory membrane, the longer it will take for the oxygen molecules to get from the alveoli into the blood. But luckily, the wall is very, very thin, so it doesn't cause much trouble as the red blood cells flow past an alveolus. The oxygen very quickly diffuses in. But if that respiratory membrane starts getting thicker because of swelling, water, edema it's called in the lungs, then that thickness is going to become meaningful and it's going to start to interfere with gas exchange. It also depends on the solubility of the gas, which is caught up in what's called the diffusion coefficient. We'll mention something about that in a bit. And it has to do with the partial pressure difference. The greater the difference in partial pressure on either side of the membrane, the faster diffusion happens. That's analogous to concentration gradient. The greater the concentration difference of a solute across the cell membrane, for example, the faster diffusion will take place across that membrane, and it's true also of gases across the respiratory membrane. So let's take a look at the partial pressure of gases in different parts of the system, the alveoli and the blood in different regions. Well, it seems like a lot of boxes at first, but you'll see that a lot of these boxes are identical to each other, and so there's nothing new to discover there. So here, this pink box up here is looking at the partial pressure of oxygen and CO2 in the air we inspire. Then we are going to bring that air down into the alveoli, and let's see what the partial pressures are in there. Partial pressure of oxygen in the alveolus is only around 104 millimeters of mercury instead of 159. Why would it be so much lower? Because, for one thing, that dead space volume. When you inspire some fresh air, the first thing that happens is 150 mils of old air goes right back down into the alveoli, and it doesn't have very much oxygen in it. It's already been depleted. Then fresh air goes in behind it, but when you mix those two together, it dilutes this 159 millimeters a bit. Also, we're going to add some water vapor, another gas, which is going to displace all the other gases in the mixture, in the air mixture, because when we bring in the air, it's kind of dry, and then when we bring it in through the nasal cavities, they will humidify the air to saturation. It'll be like the hottest, most humid Florida day in there, and we'll have a very water-saturated environment. That's good. We don't want to dry out the respiratory membranes as the air comes down in. All right. So then we bring some blood from the veins coming out of all the tissues of our body. They enter into the right heart. The right heart pumps that venous blood, that oxygen-depleted blood, through the pulmonary circulation, and as that blood passes by the alveoli, it becomes equilibrated. It exactly matches the alveoli. So the alveoli contain 40 millimeters of mercury partial pressure CO2. We'll talk more about that in a second. That's the low number. And that's the arterial blood is going to exactly match that. So the arterial blood has around 100 millimeters of mercury partial pressure of O2. That 95 is a little pessimistic, closer to 100. That maybe 95% saturated. We've got about 100 millimeters of mercury partial pressure of O2. CO2, 40. It exactly matches the alveoli. The difference in this 95 versus 104, you can just ignore that, is because there's a small volume of blood that comes from the left heart that goes to the lungs to oxygenate all the structures in there. It's not part of the pulmonary circuit. It comes from the left ventricle through this big artery, say, and then a branch goes right up here to oxygenate this tissue, and then right back into the aorta. Holy mackerel. And so that's putting some already used blood in with the fresh oxygenated blood that's coming in here, and so we end up with that lower number. Just so you know, but just think of the alveoli and the arterial blood coming out of the, call it arterial blood because we were talking about the systemic circulation. The blood coming out of the lungs exactly matches the alveoli. Okay, so we're going to take that blood into the left side of the heart, pump it out to all of the capillaries in your whole body. The tissues, the fluid around the tissues has only 40 millimeters of mercury oxygen partial pressure at rest because the cells are always extracting oxygen and utilizing it for their cellular respiration. And they've been producing CO2, so now we have 46 millimeters of CO2 partial pressure. And we bring this oxygenated blood into these blood capillaries and diffusion starts to happen. And by the time the blood leaves the capillary beds throughout your body, it exactly matches the fluid in the tissues. 40 millimeters of mercury partial pressure oxygen, 46 of CO2. Now this is at rest, not during exercise. So we take that blood that's been depleted of oxygen and added some CO2, carry it to the lungs, and as we bring it to the lungs and pass it along the alveoli, it will come to exactly match the alveoli once again. So we really have only one box of partial pressures to learn over here, because these are the same, and one box here. As the blood passes through the tissues, it will equilibrate or match the tissues. So the tissue fluid and the blood coming out of the capillary beds are exactly the same. So again, the pulmonary circuit, we've already taken a look at that in that previous diagram. It's this circuit going to the lungs. The systemic circuit is the lower circuit going to all the tissues of the body. Well, interestingly, it turns out that the blood flow in different regions of the lung is not balanced. It's not the same. Well, because of the gravitational force pulling downward on blood, it's much easier to push blood through the lower parts of the lung. It's hard to pump the blood uphill to the upper parts of the lung. So the lower parts of the lung have more blood flow. That's called perfusion. There's greater perfusion at the bottom of the lungs or base of the lungs, less perfusion at the top or the apex at resting conditions. During exercise, we're going to balance that out. We're going to have so much blood flow through the lungs at an elevated pressure that we're going to have a more evenly distributed flow. So here this graph shows you the blood flow in different regions of the lung from bottom to top. So at the bottom of the lungs, here's the blood flow. Highest in, say, liters per minute. As we go up higher and higher, rib by rib, the ribs are numbered from top to bottom. So now we're getting up to the top of the lung, the apex of the lung. The blood flow is much lower. So point is, we have an uneven distribution of blood flow to the lungs. And this is yet another diagram showing the two circuits. The pulmonary circuit, in this case, showing to the sides a little bit more sort of anatomically correct. The systemic circuit, upper parts of the body, lower parts of the body, and so forth. So another interesting thing, the ventilation is also not even from the bottom to the top of the lungs. Ventilation is greatest at the bottom of the lungs, as is perfusion, and least at the apex of the lungs at rest. And so there's a consideration to be made physiologically. What we'd like to see is, we'd like to see a balance between perfusion, blood flow, and ventilation, good oxygen delivery, so that we can get plenty of oxygen into all the blood. That's called the ventilation-perfusion ratio. And the ideal would be 1, an equivalent amount of blood flow and oxygen delivery so that we can fill the blood up with oxygen easily as it passes through the lungs. But at rest, in the upright position, the top of the lungs or apex of the lungs are underperfused relative to ventilation. And so we'll have a ventilation-perfusion ratio of less than 1, not good, not ideal. The base of the lungs, it's overperfused. There's more blood flow than oxygen, than air delivery or oxygen delivery. We have a ventilation-perfusion ratio of greater than 1. Now during exercise, we're going to improve that ratio and that's ideal. So many things that happen during exercise, some wonderful changes happen in your body that allow you to maximize the delivery of oxygen into the blood. The ventilation-perfusion ratio becomes nearly perfect throughout the lungs during exercise, during most exercise rates. At extremely heavy exercise, you may actually develop a ventilation-perfusion inequality, and that's going to be part of the limitation of our ability to deliver oxygen to the muscles during exercise. But at maximal exercise intensity, that's not such a problem because we're already doing mainly anaerobic respiration in the muscles anyway. We'll have plenty of time to get oxygen out to the tissues when we stop to rest, which will come very soon. This is just a cool, you had to memorize this obviously, but just to show you, the ventilation at the top of the lungs is 0.24 liters per minute, 0.82 liters per minute at the base of the lungs. Look at that's somewhat different, less than fourfold difference. Look at the blood flow. 1.29 liters per minute of blood flowing near the base of the lungs, 0.07 liters per minute at the apex. So now if we calculate the ventilation-perfusion ratio, we'll see that it's greatly different in different parts of the lungs. We have underperfused apex and overperfused base of the lungs. So we don't have an ideal ventilation-perfusion balance in the resting lung, the top or the bottom, but during exercise we'll have a much better ratio. How about oxygen transport in the blood? How do we do that? That's a whole other topic. We transport oxygen in the blood bound to hemoglobin. Each hemoglobin complex, which is what the red blood cells are packed full of, can carry 4 oxygens. And as the blood travels through the lungs, we're going to saturate all of that hemoglobin, and we're going to put 4 oxygens on every hemoglobin in the lungs as the blood flows through the lungs and then send that to the tissues. This is just talking about the actual amount, the number of milliliters of oxygen per liter of blood. I think the biggest takeaway from this is to realize what's the percent of hemoglobin in the blood. Percent hemoglobin in the blood is around 15% in males, around 13% of the blood is hemoglobin in females, and that's what limits the amount of oxygen you can stick in there. You can stick 200 mils of oxygen per liter of blood in men. That's because that's how much hemoglobin, how much the hemoglobin can hold. 15 grams of hemoglobin per 100 mils of blood, 150 grams per liter, and you multiply that times the mils of oxygen per gram of hemoglobin. So the hematocrit is the percent of hemoglobin in the blood, and that's what determines the amount of oxygen that can be carried. You don't need to memorize the amount of oxygen that can be carried, but do know that it's the amount of hemoglobin that determines how much oxygen can be carried. If you don't have enough red blood cells or they don't have enough hemoglobin in them, then you're going to have an insufficient carrying capacity. You won't be able to carry enough oxygen in your blood. So deoxyhemoglobin is what we call hemoglobin that doesn't have oxygen bound to it, or it doesn't have 4 oxygens per hemoglobin. Oxyhemoglobin is the saturated hemoglobin, packed full of oxygen. So here's the challenge. We're going to bring the blood to the lungs, and we want to attach oxygen to the hemoglobin in the lungs, completely saturate it, then send that hemoglobin over to the tissues and still be able to get the oxygen to come off again. And the reason that works is because there's a big partial pressure difference in opposite directions in the lung versus in the tissues that will drive diffusion. And we have changes in affinity, changes in the grip of hemoglobin for oxygen in the lungs where it's high affinity versus in the tissues where the affinity is reduced. That's why it works. We change the affinity of oxygen for hemoglobin as the hemoglobin goes over to the tissues and blood capillaries. This is called the oxygen-hemoglobin dissociation curve, and it shows what its shape depends on the peculiar properties of hemoglobin. It's very unusual stuff that allows us to do what we do. We take for granted what we can do by way of activities, and the reason we can do what we do by way of activities is because of the properties of hemoglobin and oxygen binding. Couple things to note about this graph to sort of understand what it's telling us. One thing is, at the bottom axis, the x-axis I meant to say, is the partial pressure of oxygen. On the y-axis is the saturation of hemoglobin. In other words, if we take some hemoglobin, get a mitten full of hemoglobin, and stick it in a chamber filled with 100 millimeters of mercury partial pressure oxygen, what will be the saturation of hemoglobin? 100%. So in our lungs, what happens? We have 100 millimeters of mercury partial pressure of oxygen, right, coming from the alveoli. Saturate the hemoglobin. Now let's take some of that saturated hemoglobin over to the resting tissues. There's only 40 millimeters of mercury partial pressure there. What's going to happen? Some oxygen is going to escape because at 40 millimeters of mercury partial pressure oxygen, the hemoglobin is only 75% saturated. So as we remove the blood from the lungs to the tissues, 25% of the oxygen comes off, and then we send that blood back to the lungs to be reoxygenated. Isn't that interesting? At rest, you're only using 25% of the oxygen that your blood is carrying. There's a lot more to be had. Let's say we start exercising. Rats, I don't have a picture that I wanted. When you start exercising, the partial pressure of oxygen in the tissues, or in the muscles, is going to be only maybe 20 or even 15 millimeters of mercury partial pressure of oxygen. Because the muscle cells are extracting more oxygen, taking out of the fluid. The partial pressure is dropping. So let's take our hemoglobin from the lungs down and move it down to 20 millimeters of mercury partial pressure oxygen. The saturation now is only 20%. So all you have to do is start your muscles working, start them taking oxygen, and as they do so, lowering the partial pressure, fully 50% or more of the oxygen available in the blood comes tumbling off the hemoglobin available for the cells. This steep slope of the hemoglobin-oxygen dissociation curve is what makes that possible. The more oxygen that comes off the hemoglobin, the lower its affinity for the remaining oxygen. So as we lower the partial pressure of oxygen around the hemoglobin, oxygen just comes tumbling out. So all we have to do is make a small drop in partial pressure in the tissues during exercise of oxygen, and the blood will deliver a huge bonus of oxygen diffusing out into the tissues for use by the muscles. So that gives us this tremendous reserve of oxygen in the blood flowing through all the organs. Then we send it back to the lungs for oxygenation. We also said that this whole thing works well because other things, we're going to see other things that affect the affinity, making it high in the lungs and lower affinity in the tissues. One of those things is the pH of the blood. In other words, that's because of the pH of the body fluids in the tissues. Let's say that hemoglobin dissociation curve we were looking at before is in the middle here at pH 7.4, neutral body pH. In the tissues, the pH is more acidic, say 7.2. And so for any given partial pressure of oxygen, let's say 40 millimeters of mercury right here on this line, if we take that hemoglobin and just transport it to the tissues where it's more acidic, you can see we're dropping in saturation. That's because the affinity of hemoglobin for oxygen will drop at acidic pHs. And then when we go into the lungs, it's actually more alkaline. And so in the lungs, we have the maximum affinity for oxygen. In the tissues, we have a lowering affinity. Oxygen can get away for the use by the tissues. Another thing is the body temperature. The temperature in the lungs is cooler because we're bringing in cooler air. It's largely warmed up as it goes into the lungs, but it's still not body temperature in the lungs typically. And so at this lower temperature, the affinity of hemoglobin for oxygen is high. And as we take that blood from the lungs here and heat it up to 37 degrees or even 42 degrees in working muscles, it just gives so much energy. The oxygen just rip their way free from the hemoglobin. The hemoglobin affinity, ability to hold that oxygen, is diminished, and oxygen comes out in the tissues. Good binding in the lungs, good delivery, good dissociation in the tissues. All right. One last thing about that before we look at carbon dioxide. Myoglobin is a pigmented red complex, much like hemoglobin in red blood cells. It's an oxygen binding complex, but it binds with even more affinity than hemoglobin. So another thing that helps your muscles get the oxygen they need is the type 1 aerobic fibers have lots of myoglobin, red myoglobin, and it grabs oxygens and holds on tight, and then we'll deliver it to the mitochondria for cellular respiration. So here we can see the dissociation curve, the oxygen dissociation curve of hemoglobin, myoglobin. Wow, look at this. Myoglobin, even at very low partial pressures, can be saturated with oxygen, has a super high affinity for oxygen. How about CO2 transport? Whole different story. Cells make CO2, it diffuses into the blood. How does it get from the blood to the lungs? Let's take a look. CO2 is 20 times more soluble in the body fluids, in the plasma, in water, than oxygen. So a significant amount of carbon dioxide is dissolved in the plasma, 10%. Oxygen, you divide 10% by 20, 0.5% of this oxygen can be carried that way, not really significant. All right, so 10% of oxygen dissolved, 20% of the CO2 can, I meant to say CO2, 20% of CO2 can bind to hemoglobin, can stick to all the side chains of the protein, not to the oxygen binding site, but stick all over the hemoglobin protein. There's so much of it, it can bind up a bunch of CO2. But the majority, greater than 2/3 of the excuse me, CO2 is carried as bicarbonate ion in the world. Here's the CO2 being produced in the tissues. It's going to be combining in the red blood cells with water by the action of an enzyme called carbonic anhydrase, and that's going to convert it to carbonic acid, which the 3 was supposed to be a subscript. And then carbonic acid dissociates, producing hydrogen ions and bicarbonate ions. And now you can see why the pH is more acidic in the tissues. All that extra CO2 being produced is being converted to hydrogen ions, acid, and bicarbonate ions, which will then diffuse out of the red blood cells and be transported to the lungs. That's what we mean by being transported as bicarbonate ions. Physically, yes, as bicarbonate ions. Here's a graphical a cartoon representation of that. Here we have CO2 being produced in the tissues. 10% can dissolve in the plasma, the blood plasma, be transported to the lungs and diffuse into the alveoli. Here we have it diffusing back from the blood into the alveoli in the lungs. 20% can stick to the hemoglobin, and then that will dissociate from the hemoglobin because the concentration gradient or partial pressure gradient is the opposite way in the lungs. Then finally we see CO2 being converted to carbonic acid by the action of carbonic anhydrase enzyme, and then dissociating to form hydrogen ions. The bicarbonate diffuses out into the blood, transported to the lungs, convert the carbonic acid back into CO2 and diffuse into the lungs. So CO2 is transported as bicarbonate ion largely. So here's another way of looking at these reactions. When you are in the lungs, we're going to take away CO2, right? In the lungs, we're going to let the CO2 breathe out. So we're going to take away something from the left side of this equation, and that's going to draw the equations like a swing to the left. And we're going to use up that bicarbonate, convert it back to CO2, and breathe it out. Then when we get to the tissues, the cells are producing a lot of CO2 or piling up something on the left side of the reactions, and that will push like a plow, push the reactions to the left, to the right, like again like a swing, and we're going to convert that CO2 to bicarbonates, which is these reactions swing back and forth as the blood goes from the lungs to the tissues and back. Another thing that we should note is that the greater the ventilation rate, because we're bringing in fresh air with no CO2, the lower the partial pressure of CO2 in the blood, in the body. Right? The faster we ventilate, the more we're going to blow out that CO2, the more the swing is going to swing to the left, and we're going to use up bicarbonate, and the amount of CO2 is going to go down in the body. The slower the ventilation rate, CO2 is going to accumulate in the body. I'm not going to be getting rid of it as fast as the cells are making it, and see a partial pressure of CO2 will rise. So join me next time as we work our way a little deeper into the discussion of pulmonary changes during exercise. What's going to happen to all these basic principles we've learned when we start exercising?